Hi class. So we are starting chapter 11, acids and bases. This is the first section, 11.1. So we're going to look into what are acids, what are bases, there's different types, and how to name them. So for instance, soft drink contains phosphoric acid and carbonic acid. We're going to look at how are these named like that. So the first thing we're going to start out with are Arrhenius acids. There's different type of acids. This is the first one that we're covering. These Arrhenius acids produce hydrogen ions. You can also call them protons when they dissolve in water. So here's a simplified way of looking at it. We have hydrogen chloride. It's a gas, so there can be hydrogen chloride as a gas, but when it comes into contact with water, it is aqueous. It is now an acid. So what happens is that it disassociates completely, 100% broken apart, if that's what, and make it easier to understand. So we have the proton ion and the chloride ion, anion, floating in water. This makes it an acid. Now this is simplified. In the next section, we'll look at why this is not really, we write this as more of a shortcut. It doesn't really happen this way. What it does is happens more better in this picture where we have HCl and it comes into contact with water, and the hydrogen actually comes into contact with the water and now becomes a hydronium ion, which is H3O plus and then chloride ion. This is more of what it looks like, but we can also write it like this. They mean the same thing, but if you're asked for something regarding like homework or an exam, make sure that you understand which way it's being asked for, and it'll usually give you hints. The hints are the way to understand how to answer it. So because they disassociate, they are electrolytes. They produce the proton in water, so they are broken up into a cation and an anion. Acids have a sour taste. You would know that if you've ever tried to eat a lemon. I love lemons, bad for the teeth, but love the sour of them. Vinegar is another. Vinegar is acetic acid in water, and it's very, if you've ever tried to taste it, it's very, very sour. Acids turn blue litmus paper red. Let me explain what that is. This is litmus paper. These are, it's a kind of drawing. These are litmus paper. And you would, in order to check if you had an acidic solution, because the solutions are clear, you cannot tell if it's water, if it's, and you never want to, in chemistry, you never taste anything, or you never just stick your finger in anything. You would get litmus paper. And let's say that you think that the solution you have is acidic. You would grab a blue litmus paper. The blue litmus paper is basic, and it will react with an acidic solution by turning it red. And the opposite for base. If you think you have a basic solution, you would grab a red litmus paper, which is acidic, and it will turn blue if the solution is basic. And as you see in neutral is because the red litmus paper is already acidic. So if you dip it into an acidic solution, there's no change, nothing happens. And the same goes for the blue litmus paper. If you dip that into a basic solution, there's no change. So only when they are put in their opposites will they change. If a blue litmus paper goes into an acidic solution, it will change to red, and a red litmus paper goes into a basic solution, it will turn blue. So that's what this is saying, is that if you stick a blue litmus paper in, the litmus paper will turn red. These are very common in labs. Had we been in lab, you would have had to test this. It's very simple. And some metals can, some acids can corrode metals. That has to do with, if you can remember, the single replacement reaction. Okay, so we've covered this. Now, naming the acids. The acids are a little different. There's not a big difference in them. There's basically two separate rules you have to remember, but they can get a little overwhelming if you don't practice it. So acids have a hydrogen attached to them before they disassociate. So we have to let you know the difference between, for instance, if we look here, HCl, if this is a gas, in this state it's a gas. So this is hydrogen chloride. It is not hydrochloric acid because it's a gas. Now, if we were to have an AQ here, that tells me this is hydrochloric acid. So for reactions like this is why it's really important to have the physical state. But what if you're not given the state? Then you need to have something more that will tell you. For instance, you see here, here's the aqueous. So this is going to tell you this is hydrochloric acid. Well, where did the naming come from? The naming, when you have something that is a simple nonmetal. So this is, for instance, halogens tend to be a good group to focus on when you're looking at acids. There's just one, and it's a nonmetal, so halogens. So we take the chloride, it's with the hydrogen, and it's an aqueous solution. You add a prefix of hydro, and then you change the ending, which would be chloride, to ic acid. So this is now hydrochloric acid instead of hydrogen chloride. It's hydrochloric acid. For instance, if this was an I here, it would be hydroiodic acid, hydrobromic acid, hydrofluoric acid. So you just change the ending and you add a hydro in front. That lets you know this is an acid. There's one exception to the rule. We have cyanides, which is a C and an N, and you can tell this has, it would be more considered of a polyatomic ion. However, we don't name it as a polyatomic ions are. So it's the only exception to the rule of simple nonmetals and naming acids. So we add the same rules, hydrocyanic acid, to this one. So this is the only polyatomic ion that is fitted into the rules of a simple nonmetal to name them. Now, acids with polyatomic ions are not as difficult, or maybe sometimes they seem a little bit more difficult than a simple nonmetal. What we do is we don't add hydro in front. Do not add hydro in front unless the hydro is already there for that compound before it became an acid, and it won't be. Then you don't do anything to the front. You only change the back ending. So if you have a word that has an ate at the end, you change it to ic acid, which is the same for simple nonmetals. If it's an ite, remember this ate and ite has to do with how many oxygens a compound has. The lower amount of oxygens on a polyatomic ion have ite, and the compounds that have higher amount of oxygens are named ate. Sulfate, sulfite, nitrate, nitrite. You change the ate to ic acid. Chlorate is now chloric acid. There's no hydro in front because you don't want it. If you add the hydro in front, it's HCl, not HClO3, as we're looking at here. Ite to us, os. How are you? Os acid. For instance, you have chlorite. This is chlorus acid. That tells you which oxygen compound with an oxygen, oxoanions is what the term is, which one you're dealing with. So here's a list here of both on here. You have fluoride. It's a simple nonmetal. It's a halogen. So you're going to hydrofluoric acid. We've already covered hydrochloric acid, hydrobromic acid. It's a bromide. It's a bromide with an H added to it. So hydroiodic acid. Again, cyanide is the only polyatomic ion that's considered naming as like a simple metal. And then you get into the polyatomic anions. And in this case, we could look at nitrate. Because it's an 8, you change it to ic acid. So it's HNO3. This is nitric acid. We have nitrite, which is NO2 minus. This is, add an H to it, and it's nitrous acid. And remember, when you add an H to it, the charge goes away because it's balanced now. Sulfate, add an H to it. Actually, in this case, you need to add 2 of them to it, and it's going to be sulfuric acid. And sulfite, add 2 H's to it, sulfurous acid. Carbonate, carbonic acid, and that is with 2 H's, 2 protons added. Acetic acid from acetate. And then we have phosphate, which has 3, so you have to add 3 to it, phosphoric acid. And we have phosphite, which you add 3 again. And this is phosphorus acid. And here I put together a table so you can see oxoanions and where the terms come from. Remember, the 8s at the ending identify with more oxygens, and the ite ending identifies with the lower amount of oxygens for that compound. The hypo and the per identify with the lowest and the highest in between. So this will give you an idea, and the same thing goes for bromite. Same as chloride. These are halogens, and then we can put their oxoanions, and you can see how they're named and with their acid. So the names don't change. You just change the ending based on what they originally are already called. So let's take a look at these and go through some naming. So we have HBr. So this is a halogen. It's a non-metal, and it's a simple non-metal. So this means automatically 2 of these are going to be kicked out because we need to add hydro to the first part. So A and B are gone, and this is going to be it's not hydrogen bromide, it's hydrobromic acid. We changed the "ide" to an "ic" acid. And now here we have H2CO3. So remove the H's if you have problems figuring out what this is. Only look at the compound here, and this is carbonate. An 8 acid, it's polyatomic ion. So you are not going to add any hydros to the front. You're simply going to change the ending based on how many oxygens it has. And the key thing here is just know what the name of the polyatomic ion is and add "ic" acid or "us." And in this case, carbonate is, carbonic acid. We changed the 8 to "ic" acid. And then here we have one that is HBrO2. So hydro B is already out because we are not going to deal with anything with hydro. It's not a simple nonmetal. So if we look here, we have bromis acid. It's a bromite. It's not a bromate because we have a BRO. If you take a look here, we have a BRO3 minus, which is bromate. We are looking at bromite. So this is going to be a bromis acid. Mite will be changed to us acid. Okay, so now let's take a look at bases. We have Arrhenius bases. The key thing about Arrhenius bases is that when they dissociate into hydroxide ions and a cation. So think of sodium hydroxide. A lot of these, not all, but they mostly are group 1 and group 2 metals. So we have lithium hydroxide, calcium hydroxide, sodium hydroxide. What was the other one? Did I say lithium hydroxide? And I thought I had one more, but I can't think of it right now. Potassium hydroxide. That's just some. But you do have some a little bit that are, aluminum hydroxide is one that's not a group 1 or group 2, but it's also here. But they are only group 1 and group 2 metals that they are attached to. They are electrolytes because they produce hydroxide ions in water, and it's 100% dissociation. So these are strong electrolytes. They're very soapy and slippery. This is bases are what we use to clean our clothes with. Also, some of the other things that you probably come into contact with or you're familiar with is antacids. If you have an heartburn, you will take something that's usually made of calcium hydroxide, magnesium hydroxide, something like that, and it will, what happens is your stomach turns out an excess of acid. So more than stomach acid than what you need, and it starts coming up, and that's why you feel it kind of down in, the middle of your chest. And when you take an antacid, it neutralizes the excess acid. It doesn't remove the stomach acid, but it neutralizes the excess acid. So let me see, drain cleaners. I'm trying to think of what some of the things are. Oven cleaners, so something like that. So they're soapy, they're slippery. They turn litmus indicator paper blue, because remember you would use a red one, and if it's blue, if it's a solution that's basic, it will turn it blue. And phenolphthalein indicator pink. We haven't touched titrations yet, but you will start with an acidic solution, and you will add a color indicator, which is clear, because we're going to cover pHs. And as the pH rises, when it hits to a basic condition, it'll turn that whole solution pink. I'll explain more of that later. But so this is the difference they produce. The main thing is where we were looking at Arrhenius acids, they produce proton hydrogen ion in an aqueous solution. These produce hydroxide ions. So naming bases. Typical Arrhenius bases are sodium hydroxide, potassium hydroxide, barium hydroxide, and aluminum hydroxide. So here's some, and you can see that 3 of these are from group 1 or group 2 metals, and the third one is from a group 3. Calcium hydroxide, you can see here, is used in the food industry to produce beverages and in dentistry as filler for root canals. At first, when I saw this picture, I thought it was a foot. I thought it was toes for a second, and then I realized it's got fillings. This is a tooth. Just quickly looked at it. Okay, so let's do some quizzing here. So this, I don't have it broken down. I have this all on one page. So we're going to go through all of these. So we have HNO2. So HNO2 is We have an H. It's a polyatomic ion. So before you even look, remove the H if it helps you. So we have, but we know that this is a 2 and a 3 exists. So this is not nitrate. This is nitrite. So nitrite is going to have an OUS acid in naming. So it's going to be D. This is nitrous acid. Calcium hydroxide, that's pretty easy. E. Now here again, if you get stuck, don't look at the H's. This is sulfate. So sulfate, the ending changes to ic acid. So this is sulfuric acid. And here we go. We have another polyatomic ion. This is not by itself. So this one is going to be iodic acid. And then we have sodium hydroxide. So this is E. So hopefully these will start making sense the more you look at them. And there's the answers. Okay, so here is a table of acids and bases, Arrhenius acids and bases. Acids, Arrhenius acids produces a proton in water, in aqueous solution, let's say. It is electrolyte. Both are electrolytes. Bases produces hydroxide ion. Acids are sour. Think of citrus fruit. Where bases are bitter and chalky, and think of an antacid, or, you know, if you've ever taken something like Pepto-Bismol, kind of has a very chalky taste to it. If you acids will sting and bases will feel slippery or soapy. Litmus paper will turn red, and bases it will turn blue. And phenolphthalein, which is a nice fun word, is colorless in acid. It's a solution. It's a color indicator to tell you what the solution is. If you drop a few drops into it, it's clear. If it's acidic, it will stay clear. If the bases, then we'll cover what makes an acid and base is pH. And if the pH is above 7, that's considered basic. And as it starts going into 8 and so forth, it will turn pink. The solution will just turn pink. And the more basic it goes, the darker pink it becomes. And acids are neutralized by bases, and bases are neutralized by acids. That's why you take an antacid. It will neutralize that extra base that is, the extra acid that's built up in your stomach. Okay, so A is an acid and B is a base. So let's take a look at these here. Has a sour taste. That's an acid. Think of lemons. Think of, citrus fruit. And 2 produces hydroxide ions. That's, of course, a base. Has a chalky taste. Think of Pepto-Bismol. When I was a kid, I used to have to take Maalox. I don't even think that exists anymore. But I take antacids. When I was pregnant, I had heartburn every single day. So I took antacids all the time. And it's chalky. So B. And then 4 is tricky because both are electrolytes. So it's going to be A and B. Because remember, they both dissociate. When we're dealing with hydroxides, those dissociate 100%. Acids, on the other hand, they are electrolytes, but they're strong acids, and there's weak acids, which we haven't covered yet. But they're still electrolytes. And then produces protons or hydrogen ion in aqueous solution. That's A. So 4 is A and B, and 5 is A. That's it.